Okay, consider a system. You are given a differential equation y dash is equal to some function of x and y, and some initial condition that y of x0 is y0. So this is your differential equation, or you may write it in this form: dy by dx is equal to f of x y at, or y0 is given, y at x0 is y0. So this is your system, given system. Okay, so you have to solve this equation numerically. You have to obtain a solution numerically. Now I'm giving you some point, some xn, and you only know the value of the function y at x0. This is your x0. Now I'm asking you to find a value at some other point xn, which is which has some distance from this original point, and you only know the value at this point, that is y0. Now you have to find this yn, and also in for the value at in between points. So how will you construct your numerical scheme to solve this question? So if we go for the Taylor series approximation of our original solution, original function y, let's say y is my original function, and if I go for the Taylor series approximation of this, I will look at its value at that point, that's y at x0 plus x minus x0, y dash of y dash at the point x0 divided by 1 factorial plus x minus x naught square by 2 factorial times y double dash of y double dash at the point x0 plus so on. So this is your Taylor series approximation of the original function y. So what you can do is that you can truncate after certain point, certain terms. You can, after certain few number of terms, you can drop other terms. Then you can do the truncation. Let's say we will go for the, if we go for the just first, after first term, our y will be just will be y of x0, which is just a constant number, which means you were having some solution to your original problem. This was original y of x, and you know the value that this is y0. Now you are approximating by the just a line, horizontal line. You are saying that your solution is of this type. So this is when you retain only one of the term of the Taylor series. But your function need not be a constant, it may be varying, right? So let's retain two terms of the Taylor series. Now your y of x will be y0, y at x0 plus x minus x0. This will be approximated by this, and the derivative y dash at x0. So this is the approximation when we retain after only two terms of our Taylor series approximation. But what do you know about y dash at 0? Your original differential equation is this. This is your differential equation. This derivative you already know. So y dash at x0 will be f of x0 y0, right? We can find this value because we are given the differential equation, right? So from this, your scheme is y at x is y at x0 plus x minus x0 times f of x0 comma y0, right? So now let's say I want to calculate at the point x1, which is at a distance of h from the x0 point, that is, this is x0 plus h. Now I can write x1 minus x0 as h. So y of x will be y at x0 plus this. I can write, let's say y at x1 I am calculating, then I can write this x1 minus x0 f of x0 comma y0. Now you can use this value x1 minus x0 as h. So y1 which is y at x1 is approximated as y of x0, y at x0 plus this is h, the step length f of x0 comma y0. So your value at the next point is, you can write it in a numerical scheme. It depends on the previous value and the step length and the derivative, the value of the derivative at that point. So this is now you can go for other points also. So this is, let's say this is x0 and this is your xn. You are moving some steps. This is plus h, x0 plus h, that I call x1. There may be x2, x3 up to so on, xn minus 1, and this is xn. So xn is x0 plus n times h, n steps ahead from the point x0. So you can calculate the value at any arbitrary point yi, means at any point yi. This can be written as yi minus 1 plus h times f of x I minus 1 yi minus 1. So this will be your general formula at any point, right? So now you can calculate y2, y3, the value of y at all these points, right? Is it clear till now? So this is Euler's method. This way of finding the value of yi's is Euler's method. What actually you are doing, you have the original system. Let's say this is the kind of possible solution. What Euler's method is doing, you are doing the discretization of the system at these points. This was my x0, this is my xn. Now what you are doing is, your method, Euler's method, is connecting these points with a line, and this is the distance of h. So this is line approximation of the original function. Now as the step length reduces, then this solution will converge. It will it will approximate your original function. That you can check when we change the step length. Is it clear what this method is doing? Any questions till this point?
Clear.
Yes. Okay, so this is your Euler's method. So based on how many terms you retain, you get your value. Now let's try to solve one problem with this. So question is, find y of 1 for the initial value problem, and the problem is dy over dx is x plus y, and your value at x0 is 1. So you have to find the value at y1, given that y0 is given and your differential equation is given. Now what you can do is, this is your 0, this is your point 1, desired point where you want to find. Now one way is to just directly jump from this point to this point in the Euler scheme and find the value, which means you are just taking the distance between these 2 points as your step length, right? That is one of the way. But sometimes I will specify what's the value of h you have to use. What is the value of h you have to use? In this case, we'll be using 0.1. If it's not known, you can directly jump from this point to this point. Y1 can be just y0 plus h is the distance between these 2 points, that is 1 minus 0, and f of x comma y is, this is your f of xy, which will be 0 plus, and y0 is 1. So your y0 was already 1, so this will be 1 plus 1 2. So you are directly jumping to this point. But when I specify my h, now you have to take these many steps. Now this will be h, this will be 0.1, this will be 0.2, 0.3, and so on till till you reach the point 1. Now you have to find value at these points, and you have to reach to the value at this point. So with the h equal to 0.1, we will be solving it. Now your xn, your nth term is 1, and this will be your, in terms of x0 plus nh, your x0 is 0, so your 1, this will be, what will be this value? 0 plus nh. It will tell you how many steps you have to go for. So 1 is equal to n times h is 0.1, which means 1 by 10. So n is equal to 10. So 10 steps you have to take in order to reach that point. Now let's calculate first y1, which is y0 plus h times f of x0 y0, and if I substitute the values, 1 plus 0.1 into my x0 is 0, y0 is 1, this will be 1, and you will get the value of 1.1. Similarly, if we go for y2, which will come in terms of y1, x1, y1, this will be, what will be this value? 1.1 plus h is 0.1, and you are supplying the value f of x1 y1. x1 y1 means you are summing x1 plus y1. Your original function is x1 plus y1. This is your function f of xy, x1 x plus y. So this will be, what will be this value? 1.1 plus 0.1 into x1 is 0.1, 0.1 plus 0.1 plus 1, what is y1? y1 is 1.1, so 0.1 plus 1.1, this whole value will be 1.22, right? Similarly, you can go for y at 0.3, which is y3, which you can write as y2 plus h times f of x1 comma x2 comma y2, and using these values, 1.22 plus h is 0.1. Now x2 is what is x2? 0.3 or 0.2. 0.2 plus 1.22, and you solve this value, you get 1.362. Updating these values, you will get y4 1.53, y5 you will get now you at the end I will show you how you can write the program for this to solve for any a value of the h. So but right now we are calculating manually. y6 is 1.94, y7 is 2.19. These are the calculated values I have. y8 is 2.48, y9 is 2.81, and your y10 y10 is 3.18. So your value at your value at 1, which is your y10, that is 3.18. So this is with the Euler's method when you are taking the step length h as 0.1. Is it clear till now what we did?
Yeah, it is clear.
Okay.
Yes.
Now we have another method. This was Euler's method. Did I write the name of the method? No. So this was Euler's method. So what this method was actually doing, this was using the information at that point, at a particular point, that's xi, the value yi, and it's also using the concept of slope at the slope at that point, slope and concept of slope at that point, and the value at that point. The Euler's method is using that. Now there is another method called a modified Euler method. Modified Euler's method. So what this method, how this method is different than Euler's method, or it's also called the Heun's method. Heun's method. So in this method, what we are doing, you are utilizing the information. Let's say that you have 2 points. Earlier, you were using the concept of slope at that point in using the Taylor's approximation. Now you have, this was, let's say, x0. Now this is my x1, and these are the values of y. We don't know these values, but we are making the approximation. Now what is this method doing is slope at this point as well. Now we are using the slope at the new point as well. So if I write down the equation, now this is, let's say this was your y0 at this point, and the slope at this point we were using in the Euler's method. Now we are moving to modified Euler's method, which is using the slope at both these points. So how the numerical scheme is constructed? Now my y1 value at the point y1 is y0 plus h times, h is a step length, h by 2 actually, f of x0 plus y0 plus f of x1 comma y1. So this method is taking the average of the slopes at these 2 points. Now the important point to note here is that we are looking for the value y1, and we are also using the value of y1 on the right hand side, f of x1 comma y1. So in order to find y1, we are using the value of y1. So how can we solve this problem? So modified Euler method gives the numerical scheme this. It's using the average of the slopes at these 2 points. This is the average of these two slopes at these 2 points. But the problem is we have to find the value of y1. For calculating y1, we have to use y1. So how can you solve this problem? So modified Euler method says that you for the first case you use the Euler's method. So Euler's method is saying that your y1 is y0 plus h times f of x0 comma y0. For the first time you use this value of y1, here. You use this value of y1 here. This is with the Euler's method, normal Euler's method. Now you will get another value of y1 with the modified Euler method, and that's your new approximation. You only need to use Euler's method only once, then use the modified Euler's scheme. So we denote this by the first approximation. Then I denote with the y0 as my first approximation of y1 with the normal Euler's method, h times f of x0 comma y0. Now this was the first approximation with Euler's method. With now for the value approximated value of y1. Now this will be the second approximation, or y1 we can say that y1 or y. The upper part is saying that which approximation is this. So here we are using the first approximation. To calculate the slope, we are using first approximation, then we are updating the value at that point. Again, you can recursively use this point until the method converts. So if I write in a general form the value y1 after kth iterations at the same point is y0 plus h by 2 f of x0 comma y0 plus f of x1 comma y1, but this is k minus 1. This is the k minus 1th approximation of y1, and you have the first approximation of y1 as y0 plus h by 2 f of x0 plus f of x1 comma y1 zeroth approximation, which comes from the Euler's method. This is the first. So this is your general scheme for of using the modified Euler's method. So the concept is it's using actually the knowledge of about 2 points to construct to reach new points. It's using the slope at 2 points. Now for arbitrary yi, how can I write? So yith at 0th approximation, that is given by the Euler's method. This is h times f of xi minus 1 yi minus 1. This is at step xi, and your kth order approximation at the step I is you are using the previous point and taking the average of slopes at one point ahead and one at the current point. Plus, is it clear what this method is doing? So this will be your general scheme. So you can use this approximation, this modified Euler's method also. Now with the same value, with the same, let's solve one problem with this method also. Now you have the system dy by dx is equal to x plus y with the condition y of 0 1 and the step length h, which I am specifying 0.1, and you have to find the value at y of 0.2. So your x0 here in this case is 0, y0 is 1, and your x, the next step x1 is 0. X is your general x, the point you want to calculate value at, that is 0.2. This will be x0 plus nh is equal to 0.2. Now your x0 is 0 plus n times 0.1. This is 0.2. N is equal to 2. So this is saying with this step length you have to take just 2 steps. I equal to 1 and 2. So the first iteration you will have x1 as x0 plus h. Let's calculate with the Euler's method the first approximation y0. This will be y0 plus h times f of x0 comma y0. This will be, what will be this value? 1 plus 0.1 into your f is x plus y. X0 is 0, 0 plus y0 is 1. This is 1.1. So by Euler's method, you are getting this value by Euler's method, the zeroth approximation. Now you can use the modified Euler's method to increase the accuracy. This will be y0 plus h by 2 f of x0 y0 plus f of x1 and y1 0. So with this, what will be your value? 1 plus 0.1 divided by 2, 1 plus 1.2. What is this value coming out to be? 1.11. Now you can again improve the accuracy at this point. Now this next time you use this value as your zeroth approximation and increase the accuracy at a single point with the modified Euler's method. So this 1.1 you were getting with the Euler's method. Now with your modified Euler's method is giving you, this is by the modified Euler's method, your new approximated value. Now you can go for the second order you can go for the further improvement at the same point. This will be y0 plus h times h by 2 f of x0 y0 plus f of x1 comma. Now I am using this, the first order approximation here. Let's see how our value is changing. So if I put all the values, I will get 1.1105. Now you are moving very close to the you are approximating till other further decimal places. Till with Euler's method, you are having one value till one decimal place. With modified first iteration of the modified Euler's method, you are getting to till two decimal places. If you go for the second iteration, you are getting till four decimal places, and so on. If I use the third, remember this is not the derivative. Sometimes we write the derivative as a power, but this is the numerical scheme right now. So be careful with that. So if I go for the third order third iteration, I will get the value 1.110525. So depending on my demand, how accurate value I need, then this will be your value at your new point. Is it clear what we did? Now we have to go for the second iteration as well. Iteration second. Iteration 2, because we have to find the value at y equals 0.2, and we started at 0. We calculate the value at 0.1. Now we have to find at value at 0.2. These two value at these 2 points we calculated, and in order to improve the accuracy, we use the modified Euler's method. Now let's calculate with Euler's method your first approximation. This will be y1 plus h times f of x1 y1. We are using the updated value. This third let's say the third approximated third iteration value I am using here first time. Then the value you will get, you put all these values here. Let's say I'm using this value, then it will be 1.110525 plus 0.1 into your x1 is 0.1 plus y1 is 1.110525. This is the updated value I am using. Now similarly you will get your value at this point. So this you can simplify. Is it clear what we did in this case with the modified Euler's method? How it helps your accuracy? Yes?
Yeah. How many approximations do we need to do? Is there a rule?
How many? Can you repeat your question?
How many approximations do we need to do? Is there a rule
That
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 is
may be
generally followed?
that may be specified in the question, or see, depending on the step length, you will see, you as you change the step length, you will be getting closer and closer to your original solution. So but by if we are doing by hand calculation, then we will specify the what value of h you have to take and what order of approximation you have to go for, like whether we are looking for first order, first value, your correct value till first decimal place, your correct value till second decimal place, or third decimal place, or nth decimal place, that we can specify before actually going for this method. So that will be specified before going for this calculation. Those things will be given.
Okay.
Okay. Now we will move to the very broad very widely used method that's called RK method, or RK methods, Runge-Kutta methods. These are a family of methods where you will be approximating your function based on, now with Euler's method we were using the information of derivative at a single point. With modified Euler's method, calculated the we calculate our new value using the information of derivative at 2 points. Now you may construct new points, and uh, let me show this graphically. Now with Euler's method, we were using the derivative at 1 point. Modified Euler's method, we were using derivative at 2 points. Now with the RK method, what you can do is that you can have multiple points and the derivative at those points. You can take a weighted average of all these points and design your scheme accordingly. The way you have taken the weights of these, the weights at all the proportion of weightage you are giving to these slopes, accordingly your method will be different. Okay, so if I let's write formally. Now we will go for RK methods, Runge-Kutta methods. These are family of methods where you, for based on the weights you are giving to the slopes, the method becomes different. RK methods. So what this method is doing, that you have the IVP, initial value problem, dy by dx, as a function of x comma y. This is your IVP. Now what this scheme is assuming, that at any point, new point yi, you are calculating the value using the previous value, that's the information of yi, plus some lambda. Now what this lambda is, that's what we will see. Now this lambda is the weighted sum of some ki's, that I will say w2 k2 up to wm km, depending on the number of terms k1 k2 k3 up to km. That tells us the order of the method. Now we will first go for first order, second order. This may be the mth order RK method. So how these ki's are defined? K1 is h times f of xi comma yi. That means the slope at, you are using the concept of slope at the first point, and your k2 is a value, updated value, xi plus a1h, this will be yi plus b1, using the information of k1 also here. You similarly you will have k3, a generalized scheme you will be having, and some constants you will be getting, xi plus a2h, and you are using now k1 and k2 both again, y1 plus b2 k1 plus b3 k2, and so on. Now you will construct the value km accordingly. Now you are getting some constants a1, b1, a2, b2, b3, all these values Now, depending on how you consider the value, all these values a1, a2, b1, b2, all these values, which means you are moving, how many steps you are considering, and the slopes at those, all those points. If you specify the values, then you will get these k, the weights, and you will get what weights you have to put, and you will get your particular RK method. Let's say RK method of order 1, RK method of order 1, RK method of order 1. So what RK method is 1 is doing, we are using just value k1, which is h times f of xi comma yi, which means your yi plus 1 is yi plus your lambda, and lambda is, you are using just one term in one term. So yi plus 1, which is yi plus omega 1 h times f of xi yi. Right now we don't know the value of this omega 1. So what our Taylor series approximation says that y of x can be written as the value at y0, x minus x0 times h times, sorry, times f. This is the Taylor series approximation of value yi or y0, sorry, y of x in general. Now if you retain just the first term of the Taylor series approximation, so y at the value x1, this will be y0 plus this will be x1 minus x0, which is your h step length, and y dash at x0. So, and you will be having some higher order terms, order of h square, let's say. So if you drop your terms, this is h times f of x0 comma y0, right? This is your Taylor series approximation of the first order. Now compare this equation with your original equation. If you compare the values, let's say this was my equation 2, this is equation 3, and yeah, this is your. So what do you get from these equations? This is for general I, and this is for just one value. You can generalize this also. If you compare the value, and you will get your omega 1 as the value 1, right? You will get your omega 1 as your value 1, and which means that this your original method is just the Euler's method, normal Euler's method, which is using the slope at just one point. So RK1 method is what? Is just the Euler's method. Is it clear why this is Euler's one method, or Euler's method, RK1 method?
Yes.
Okay. Now if we go for RK2 method, so what RK2 method, now it will be using information two value, or the slope value of the slope at 2 points. So your general solution at the ith point will be, your general solution at the, let me write in a clear way, your general solution at the I plus 1th point will be using the previous information, plus now you are considering two terms, k1 plus k2, w2 k2, and your k1 is h times f of xi comma yi, K1 is this, and what is your K2? K2 is h times f of xi plus a1h yi plus b1 k1. This is your value. This is what the your RK method scheme is giving. So your yi plus 1 will be yi plus, using these values of k1 and k2 in this equation, you will get w1 h times f of xi yi plus w2 h times f of xi plus a1 of h times, and the value at yi plus b b1 k1. So this is your general scheme RK method. Now these a1 b1, these are unknown. What we are using here, we will consider the two-dimensional Taylor series of Taylor series approximation at this point. Approximate this by the two-dimensional Taylor series approximation of this function will be, what will be the Taylor series approximation of this function? So it will be f of xi yi plus a1h del f by del x at the point xi yi plus b1 k1 del f by del y at the point xi yi plus so on. So many terms will be, higher order terms will be in the Taylor series approximation of this function. But if we use this value of f in your previous equation, now your yi plus 1 will be yi plus w1 h times f of xi yi plus w2 h times, now use this value here. So this will be f of xi yi plus a1h del f by del x at the point xi yi plus b1 h f of xi yi b1 b1 k1, yeah, k1 was f of x h times f of xi yi, with k1 we have substituted here, and you have also del f by del y at the point xi yi plus so on, so many terms. Now this is your another equation. This is your equation 2, and your original equation 1 was, this was your original equation 1. Now if we compare 1 and 2, if we go for 1 and 2, you will get the solution at xi plus 1, which is yi plus 1. This is the solution at xi plus h times sorry, so this is your second equation. Okay, now your original solution is y of x, and solution to your original system can be approximated with the its Taylor series y, let's say at a point xi plus 1, Taylor series at the point xi plus 1. This will be the previous value plus h times y dash of xi plus h square by 2 factorial y double dash at the point xi plus so on. This is the general Taylor series of at y point xi, and you what you do, this is use the derivative concept here. Now y dash of I, that is your f of xi comma yi plus h square by 2 factorial. What will be y double dash here? Y double dash of xi, that will be del f by del x at the point xi yi plus del f by del y times f of x comma y at the point xi yi. I am using the chain rule here. So using this, you will get your point this is what you will get using the second derivative here. You put your second derivative here, h square by 2 del f by del x at the point xi yi plus del f by del x times this will be at the point xi comma yi. I think it should be del f by del y here, and the point f of xi yi, right? So this is your third equation. Now if you compare your equation 2 and 3, equation 2 and 3, what do you get from 2 and 3? This is your equation 2 and this is your equation 3. Both the equations are giving value at xi plus 1. If you compare now the in the equation 2 there are some unknowns w1, w2, a1, a2, and those unknowns are not present in the equation 3, but both are giving the value of xi at the I plus 1. So if you go for comparison, comparing equation 2 and 3, we get, what do we get? We will get actually a system of equations with the condition w1 plus w2 you are getting 1, w2a1 you are getting 1 by 2, w2b1 you are getting 1 by 2. Actually what you are having three equations now, three equations with four unknowns. So how can you solve this system of equations you are having, and that two yeah, so we are having three unknowns here, three equations here and four unknowns. In order to solve this, we have to substitute particular values of few variables and you will get values for other variables, which means depending on which variable you tune, you will get values for other variables as well, different values. So we have RK methods of order 2. RK methods, when I am saying, which means there's not a single solution for this system of equations. This system of equations can have infinite many solutions. You tune one of the parameter, you obtain the values for other parameters. Let's say we fix one of the variable, then we will get three equations, three unknowns, and you will get different kinds of RK methods. And if we go for the case 1, where specific values, let's say w1 is taken as half, and you will get this will result into solving other three variables. You will get w2 as half, a1 as 1, b1 as 1, and if you put all these values back to your numerical scheme, you get actually the modified Euler's method. You will get modified Euler method with these value of the parameters. Okay, is it clear what your equation is doing? So your numerical scheme will be, final numerical scheme with the modified Euler's is yi plus h by 2 f of xi comma yi plus h by 2 I have taken common. This will be value at h plus ith point, and using Euler's method at the value at the updated value. So this is what you will get. This is your modified Euler's method. Now you may have some other values, some another case. This system has infinite possible cases. But some are famous cases which have some names. For a particular values, let's say w1 is, we are tuning as 1 by 3. With this we will get w2 as 2 by 3. A1 and B1 are getting 3 by 4 value. If you go for these specific values, you will get a method, a scheme which is called Ralston and some other name is also there, Ralston and Rabi Nost, some big name is there. Okay, so this you will get with this particular choice of the values. You are fixing one variable, you are getting to from three system three equation, then you are getting the values of other unknowns. Then with these parameters you are getting a numerical scheme of yi plus 1 yi h by 3 f of xi comma yi plus 2h, not plus 2 times f of xi plus 3h by 4 yi plus 3h by 4 f of xi yi, right? So this you are getting with this particular choice of the constants, you are getting this numerical scheme. So based on how you tune a parameter, you will get different, and these are some famous methods. That's why they have some name. So this was the RK method of order 2. Similarly, you can go for RK method of order 3, and most used method is the RK4 method. RK4 method. That's mostly used. So you have RK3 method, where you are saying that my new value is yi plus lambda. Is it clear till now what we did, how these methods are working? So they are taking the weighted average of the slopes at further points. Is it clear till now what we are doing, how these methods are working?
Yes.
Okay, so now you have this RK4. I will just write the formula for RK4, RK3 and RK4 methods. The derivation will be the same in a similar way, but it will take time. But I will just write the numerical scheme, and we will also see how you can write a code for this. F of xi plus a1h yi plus b1 k1. Now you have a third term k3, which is f of xi plus a2h yi plus, now you are using b2 k1 plus b3 k2. Now this you can how you can tune these parameters. Now you will have 8 unknowns and 6 equations. So you have to fix 2 variables. You will get then the six system of 6 equations. So you will have some free variables, and you fix some of the variables, you will get different schemes. You, let's say, go for a particular value of w1. This will give you a new scheme where w2 and w3 are same, and you will get a1 equal to a2 is equal to b1 is equal to 2 by 3. So you can go for this choice, or let's say we have some free variable, let's say b2, which I am taking value 0, then I will get b3 as 2 by 3. We have two free variables, right? You have two free variables. If I am fixing this and I am fixing this, two variables I am fixing, I will get the values for other variables. So your numerical scheme will be yi plus 1 is yi plus 1 by 8, 2 times k1 plus 3 times k2 plus 3 times k3, and your k1, k2, k3 are already in the above form. So if I write it in a further simplified form, now this you will be yi plus h by 4 f of xi yi plus 3h by 8 f of xi plus 2h by 3 yi plus 2h by 3 f of xi yi, this is within this function, and 3h by 8 f of xi plus 2h by 3, and the further updated value. Okay, this is your scheme for the rk3 method. This is your rk3 method. You are using three terms k1, k2, k3 here, and the values are of these a1, a2, b1, b2. Those can be calculated using this setting the free variables to some values. You will get other equations, values in other equations. So this was rk3 method. So there is a famous rk4 methods which are which give very accurate results for solving the differential equations. I will write just the equation form of the rk4 method, then we will go for the coding part. So rk4 method. So what's rk4 method now? You are using yi value at the yi plus 1, w1 k1 plus w2 k2 plus w3 k3 plus w4 k4. Now you are using the four terms here, the value information of at 4 ki's that decides your order. So your k1 is h times f of xi yi, that is same that was used in other rk methods. Your k2 is of similar shape. Similarly, k3 is h times f of xi plus e2h yi plus b2k k1 plus b3 k2. There are some libraries which have the inbuilt rk4 method. So there you can just supply what your function f is, that will solve your differential equation. And this we are doing just for the first order differential equation. What about higher order differential equations? How can you solve your higher order differential equation? These all methods we did, they were valid for first order differential equation in initial value problem. So how can you solve higher order differential equations? Now in this case you will get 13 unknowns and 13 unknowns. There are 13 unknowns, and you have to fix some variables, and you will get your. So the classical rk4 method is where the values are calculated, which is giving you w1 is equal to w4 as 1 over 6, w2 is equal to w3 as 1 over 3, a1 is equal to a2 this is the classical rk4 method for this particular choice of these variables, and b1 is equal to b3 is equal to 1 over 2. So the idea here is you are using the slope at multiple points, and you are taking the weighted average of all those points. W6 is B6 is this. This is these were the free variables. We tune them to 0, and we get the different other variables. So the general idea is that you are using the concept of slope at multiple locations and their weighted sum. In order to get your new values, you are using the information of slope at different points and their weighted sum. Okay, is it clear till now? This is your general RK4 method with these choice of these variables. Any doubts till this point? Yes,
So the higher order, first we need to,
the higher order.
no, solving the higher order, do we need to convert it to a lower order first, or
Yeah,
and then
that's what I
apply
was
RK4?
asking. How can I showed you just how you can solve the first order and initial value problem. How, what if you have the second order differential equation whose solution is not, let's say this is y double dash plus y dash of some f of x here plus g of x y times y is, this is, let's say this is some arbitrary differential equation. How you can solve? So actually the concept is uh, an nth order differential equation can be converted to a system of differential equations of order 1, n different system of differential equations of order 1. Then you will get a system of differential equations, and those system of differential equations will be of first order, and there you can use your RK method. You are right what you are saying, that how you go for higher order differential equations.
Okay.
Okay, so if you have any other doubts in this method, you can ask me. Then after that we will go for the coding part, how you can solve. I have written the code for this, and you where you can feed your differential equation and get the solutions. Now we will move to this, how you can do it in Python. My screen is visible to you, the new part what I am showing. So how you can do it in, okay.
Yeah.
So what we are doing in this case is we use the just NumPy arrays and a plotting library. NumPy is just for handling arrays, and Matplotlib is for plotting. So I define first my Euler's method. So what you have in your Euler's method is you are having a set of points, which instead of x I am denoting with t values or the time values. So I am taking the range of values starting from your initial point to the desired point, and with a specific difference h. This is how you will get a range of values with a given step length h. Now your y I am defining another array of y values which I need to calculate, but I'm initializing those values to zeros. Np dot zeros will give me a vector of length or an array of length uh, t many values. Depending on how many input values you are taking, you will get output values at those points, but initially we are storing them, initializing them zeros. But you know that from the initial value problem that your y0 is y0, which means the zeroth, the first value of this array we know. Now you write your numerical scheme that I showed you with the Euler's method. Your updated value depends on the previous value plus the step length times the value of the function at the at this current step, previous step, right? This is the Euler's method. So you are recursively going from different values of your t values, and you are updating your yi values starting from y1, which is using y0, then you will go for y2, y3, y4, and then you are storing this, returning these values from this Euler's method. If you go for the RK method, what RK method is doing, it's again taking the this equispaced points, and it's initializing your final yi's with y0, which is given. The way I showed you how you can calculate these k1, k2, k3 with a specific choice of those AIs, BIs, which means I'm using kind of classical RK method. So k1 you use, which depends on the values of t and y. K2 is depending on k1, which you can calculate from here. K3 is depending on both k1 and k2. Uh, it's depending on k2 only, because we have taken this particular choice of the RK method. Now your updated value is just the weighted average of these values, and it returns your values. Now I'm defining my ODE as, let's say this is my first order ODE, dy by dt is minus 2y plus sine of t. This is your f now. So this is my example ODE, which depends on variable t and y. Your right hand, we are just storing the right hand side of the ODE, first order ODE. That is your for two variable function f. I am initializing the points. T0 is my 0 point and y0 is value 1. This is because we are using the initial, we are solving the initial value problem. And my t end point is 5. And till this point, I want to calculate the values with a specific step length. Let's say h is 0.1. So I call my Euler T Euler. T Euler means you are using this Euler scheme, and you are taking those steps and calculating the values at those steps. That's what your Euler's method is returning. Your Euler's method was returning t values and y values, which means your x values and y values and their corresponding y values. So those you are getting from your Euler's method. And if you go for the RK method is giving you the t values that I'm storing as trk and yrk, rk4, and example OD we are using, supplying the initial conditions and the step length. Now you are getting a point of grid system. You can plot these points, t Euler, y Euler, the scatter plot of the line plot of this, and I specify that this is my Euler method, and I also plot the RK method together with this, and this is what you will get the solution to your equation. You can see how Euler's method and how your solution of equation with RK method and how they differ, and so at most of the points they are coinciding, but at some points they are getting different values. RK method is better, as it has better accuracy as compared to your Euler method. RK4 is better as compared to Euler's method, which is just RK1 method. I showed you that your Euler's method is just RK1 method. Okay, this is about now let's solve some other equation whose analytical solution we know, and we'll compare how its solution is different than how its numerical solution is different than its analytical solution. So I have the ODE dy by dt is minus 2y. Its analytical solution, if I go manually, is y of t as exponential of minus 2t. And some initial conditions, I got the solution. Now this is my example ODE, and this is my analytical solution ODE. I will solve with the RK method with these initial conditions, and I will generate the points from the analytical solution. If I plot these points together, you can see these points are coinciding, right? Your blue dots are your RK4 numerical solution, and your analytical solution is the red line. So you can see how this discrete system is giving you the accurate solution. For this, we are able to compare with our equation, because this solution is analytically solvable. This is the way how you can compare. Now how do you solve the system of ODEs? How do you solve the system of ODEs? So your system of ODEs gets converted, your higher order differential equation gets converted to system of ODEs, the scheme remains similar. The RK method remains similar. We just, our f only changes. Now f earlier was a single value, single function. Now in the case of the multivariate setup, you will get f1, f2, f3 different values of these f, because you're getting the system of differential equations. So your RK scheme remains same, only your form of f changes. And since Python takes this, the value of f as in an arbitrary shape, it will accordingly extract the shape of f. So if I have the second order differential equation, y double dash plus 2y plus f 5y is cos of t, and if I convert this to a system of differential equation, I will get two new variables, y1 and y2. Y1 is just value y, y2 is the first derivative of your different original function, and your system becomes d of y1 with respect to time is just y2, and d2 of the second variable, which is the y1 dash, that you are getting from this equation. Substituting these values here, now you are converting your second order ODE to a system of differential equations. This is your system of differential equations, where this is your first differential equation, this is your second first order differential equation, and they have the f1 f2 corresponding f1 f2. Now your example is having two first order differential equations. You will supply this in a vector form or a list form to your original RK method, and you will get your solution accordingly. So this is your RK. In this case, we will get the solution of y dash, which means the derivative as well, but I have not plotted that. I have skipped. If you plot, you can simultaneously plot this y1 dash also, how the derivative is changing. That I have not actually, that I have eliminated from this plot. Is it clear till now how this code is working on the numerical scheme what we constructed? Any doubts till this point? No
We are
doubts?
getting the graph or values also.
Yeah, you are getting your graph. You will get a list of values, and those, if you connect with the line plot, then you will get a kind of smooth curve.
Graph.
Yeah.
Okay.
So let's try to solve the equation of the pendulum. Pendulum is having this nonlinear equation. This is the original form of the pendulum equation of the pendulum. The swing of the pendulum is governed by this equation. The dynamics of that is governed by this equation, and it is a second order differential equation. And it's a nonlinear differential equation. If we try to analytically solve this equation, we will not be able to solve it, but we can solve it using the linearization technique, where you use the concept of the perturbation analysis and Jacobian matrix. This second order differential equation is transformed into a two system of differential equations, and with certain initial conditions. Let's say the value of g is given, the length of the pendulum is given, and the initial position of the pendulum is given. We get a system of differential equations, and these differential equations we can solve with either Euler's method or we can solve with RK method. So RK method is mostly the preferred method. So RK4 method we are using here. Same function we are using. Now our only system is changing. If your new system comes, you change your system accordingly. Your RK method remains same. So if we go for the ideal case of the pendulum where the resistance of the air is not included in the system, which means there is no air resistance, then your pendulum will go and back and forth to its original place, which means it's getting a periodic behavior. So with respect to the angle, you are getting this kind of shape. But what if your differential equation, your equation of the pendulum is having the air resistance? That is another case of this dynamical system. So your system of your original system equation is now having this b times y dash, which means the air resistance is calculated with a particular choice of this parameter b, the drag air the drag due to air is counted in this model. Now your system of equations, again the second order differential equation, this you are getting into a system of two first order differential equations. If you solve this, what is the expected behavior? The pendulum will go back and forth, but its amplitude, the angle will decrease with time, right? That's the ideal in the original system. So if you plot the solution with the RK4 method, this is your shape of the trajectory of the pendulum, like the angle, how the angle is changing. Original there was some angle, and with time the angle of the pendulum is amplitude of the oscillation that depends actually on the angle that is decaying. So this is the decaying solution you are getting for the pendulum. So this is called a damped system. The system is having now the drag. This is the solution what you are expected to get, and we are getting with the RK4 method. This is giving you the decaying solution. There is a very famous dynamical system called the Lorenz system, or if you have heard about the butterfly effect. And if that is actually a system of three differential equations. This system gave rise to the study of the dynamical systems, and it's a very interesting system. You should explore this. The shape of the trajectory is very interesting. It's a three-dimensional plot, and so how this system arose was the Lorenz was modeling the temperature, the climate modeling they were doing, and they observed the strange behavior of this dynamical system. This is the system of three differential equation, and these are nonlinear differential equations. If you solve this differential equation with the RK method, you will get your solution. But the interesting thing about this system is that it's showing the chaotic behavior. The chaotic behavior means it has a sensitive dependency to initial conditions. So if you give a little perturbation to your initial conditions, your trajectory will be entirely different. So this is the three-dimensional plot of your Lorenz system, and if you change your different conditions, you will get the shape accordingly. So this shape is called what's called the Lorenz attractor. It's having kind of attractor. It's attracting trajectories, and those attractors are moving in a three-dimensional plane, and they are generating this beautiful pattern. So you can explore more about this system, or you can go for any highly nonlinear system, how you can solve that with the RK4 scheme. The scheme remains same, only your system changes. In Lorenz system, there is a three-dimensional system. Yes, anyone wants to say something?
What is the difference between this previous one and this one? Lorenz graph.
This is same, just the values of the parameters are tuned to a particular value. Actually this was to make the interactive plot. Let me run this, where you can change, where you can tune your parameters. In the first case the parameters were fixed. Now in this case I can tune my parameters, let's say for different values of sigma, different values of rho. The trajectories are getting different trajectories. The system is same. Clear?
Yes.
So you can try, you can write the code from scratch, or you can use this code what I have written, and you can play with this dynamical system, or you can play with some other dynamical systems or some highly nonlinear systems, how they are evolving with time. So it's very important to know how you can solve numerically a differential equation, because analytical solutions are not always possible, and your real life systems are always a nonlinear kind of systems, and getting analytical solutions is not always possible. So you should know how to solve your models real life more problems with these numerical schemes. So that's all for today. If you have any doubts, you can ask. Otherwise, we can conclude the meeting, today's